All right. Hello, guys. Long time no see. This is supposed to be your, I assume, lecture 12. That's on the midterm one review, which you will be taking next Tuesday. So I'll break this break that lecture into two parts. The first part will be to review, basically going through fastly on each of the core concepts in each sections. And then we'll do some examples, which I think will better reflect what I'm going to do on the midterms, okay? All right. So first of all, let me briefly go through how I would like you guys to study to better off understand the concept and to actually learn something from this course. So obviously you have to first by starting by reviewing the concepts, which are the most important thing in math, I would say so. So for example, you have to understand the definitions of each thing. For example, you have to know what is partial differentiation, what is limits, what is cross product, inner product, what is tangent space, what is gradient vector, okay? And try not to just memorize the formula blindly. The formula comes from some derivation, and I think I have tried to show the full extent of the proof of the derivation for each formula. So try to understand that and try to go through each of the intuition, conceptual ideas about those proofs and those formulas, so you guys can get a better understanding on what we're actually doing instead of just memorizing formulas and applying formulas. The second part, obviously, you have to work on problems. So we have the suggested assignment in the Stewart's textbook, right? I would suppose that you guys have already done those throughout the weeks and have get a better understanding on what we're doing. I would say that for the exercises, I would suggest you guys to finish the assignments and also the quiz problems, so you can have a better glance on what we'll be doing in the midterms. And also, if you're kind of comfortable with what you're dealing with in the assignments and the quiz problems, then you should be comfortable with it with this video, which what I'm going to go through. And last, I have put some additional exercise in the section 3 here, so you guys can go through that afterwards, after you watch this video maybe, and I'll provide the answers on campus, okay? So basically, I would have 5 to 6 problems in the midterm. I still haven't decided yet. There's like one problem I'm not sure should I put it in or not. They will break into some smaller parts, but the smallest part are really, really small. For example, there might be like part A, just verify that a point satisfies an equation, which is a direct computation problem, right? So basically 5 to 6 problems. Each of those looks like one of those in the quizzes. So I would say that you might be just spending about like 5 to 10 minutes on each. That would be an average number. And if you're comfortable with the suggested assignments and what we're going to cover in this review lecture, then you should be getting 80-90 easily if you didn't do any like algebra mistake. Okay. All right. So let's now start with our core concepts. So again, this is a review, so I won't be going through too much details, but I will just be going through like what are the important formulas, what are the important concepts, what you should know before you do the midterms. Okay. So first of all, we have 2 chapters in this midterm. The first chapter is on the vectors and the geometry of space, in particular the 3-dimensional space. In 12.1, there's not much to learn. We learn about the XYZ coordinate. We learn that for 2-point distance, it simply behaves like the 2D distance, which is you subtract the entries individually, and then you square them. Then you take square root. That's the distance, right? And we usually apply this for the 2D space and 3D space. And this is relatively not that important. About the equation for the spheres, given a center ABC, or if we're working with the plane that is AB, and you have a radius R, then the sphere with this center and this radius is given by this equation, which basically directly follows from the distance formula, right? We will be understanding more sorts of different surfaces in chapter 16. And in that case, I will introduce you guys more, but not today. And about 12.2, we're introducing vectors. So you have to know the basic operation of vectors, addition, subtraction, and scalar multiplication. So those are quite standard. And we also know that you can find out the magnitude of a particular vector, which is given by the same thing as the system formula. You square each entry, and you take a square root of them. This will be the magnitude of the vector. And to normalize a vector, to make it into a unit norm, which is norm 1, you basically divide the vector by its magnitude. And that'll be a vector of length or magnitude 1. The third section on the chapter 12 is a dot product. So we know that algebraically, the dot product is given by u dot v to be some scalar, u1 v1 all the way to un vn. In particular, we usually use it when n is 2 or 3, right? And we also know that geometrically, dot product can be used to find the angles because it can be represented as the magnitude of u multiplied by the magnitude of v multiplied by cosine theta, where theta is the angle between u and v. So in some sense, you can find out the angle between u and v via dividing u dot v by the magnitude of u divided by the magnitude of v, right? And obviously, this formula also tells you some information about orthogonality. So we know that cosine is 0 whenever theta is pi over 2, which is 90 degrees. So two vectors are orthogonal if and only if their dot product is 0. And we also have this formula for the scalar projection and the vector projection of u onto v. I believe I haven't introduced this notation, and I will not use that in the midterm because I don't really see that much in the standard textbook. So basically, this is the scalar projection, which is basically the scalar following the projection vector. So you can see that the projection vector is actually u dot v divided by magnitude of v squared to v, right? So basically, this is simply the scalar projection times the unit vector, right? So this represents both the signature and also the magnitude of the corresponding projected vector, and which is not that important. This is what we use mostly. Okay, and about the fourth section, the cross product. This is an important section which we will use a lot in chapter 16, but maybe not now. So this particular operation only exists in a three-dimensional space, so we won't introduce it for n equals to 2 or 4 or 5. So it only happens when n is 3. So you have u1, u2, u3, and v1, v2, v3. And recall that we have this nice notation of the determinant. You can write down u cross v as a vector given by this determinant, which is taking the ith component to be the determinant of this guy, u2, v3 minus u3, v2, and so on and so forth. J corresponds to this guy with a minus sign, and K corresponds to these four guys. And the geometric meaning of the cross product is basically a vector that is orthogonal to both u and v, where its direction is determined by the right-hand rule. If this is u, and we curl along v, then the sum part will be the direction of the u cross v. And we also know that the magnitude of the u cross v will be magnitude of u times magnitude of v times sine theta, where theta is again the angle between u and v. So this is a nice duality between dot product and cross product. Okay. Now 12.5, this is I would say the most important section in this chapter because we will be dealing with a lot of lines and planes afterwards. So how do we describe lines in a general space? We have to have given a point and a directional vector. So start with that point and we go along that direction. That creates a line, right? So given a point and given a line, we can represent a line, given a point and given a directional vector, we can represent a line in two ways. One is called the parametric form, x naught, y naught, z naught, plus abct, where t ranges through every real numbers. We can also write it in a symmetric form, which is like this. So basically, you are solving for t, right? T will be either x minus x naught divided by a, y minus y naught divided by b, or z minus z naught divided by c. So those are the representation of lines. Secondly, to find a plane, instead of a directional vector, we want to find a normal vector. So if you're a plane, then your normal vector looks like this. So given a point and given a normal vector, the equation is quite simple. You basically want to collect all points x, y, z. Let when you connect it with x naught, y naught, z naught, then the corresponding vector will be orthogonal to the normal vector, which is kind of obvious, right? If you are given a point, x naught, y naught, z naught, then you're collecting every point so that this vector is orthogonal to the normal vector. And if you write it down in a scalar form, you'll get A, x minus x naught, B, y minus y naught, and C, z minus z naught to be 0. And a general strategy to find this kind of equation is to find out a normal vector, which usually will be given by cross product. So that's why I'm mentioning this here. We will soon see that in the example. And the rest of the 2 points is not that important. We'll simply derive this from last in the lecture, so I put it here. So if you're working with a point and a line in 2D space, then the distance will be ax naught plus by naught plus c, where this is the equation of the line, divided by a square root of a squared plus b squared. And similarly, the distance between a point and a plane in the 3D space looks like this: ax naught plus by naught plus cz naught plus d, divided by the magnitude of a normal vector, a and b and c. Okay, so that concludes our review for chapter 12. So basically, the most important part is the 12.5. You have to know how to find out the equation and of the line and the plane. Okay. Now, chapter 14, we're into our differentiation theory for high-dimensional function. So for the chapter section 14.1, functions of several variables, the only task is to know how to describe the domain of a certain function. So for example, you have to know the definition area for, say, f of xy to be square root of x plus square root of y, then x and y must be positive, must be non-negative, right? That's the only requirement. So you have to know how to describe the domain for a particular function. And those basically go back to when we were studying a single variable calculus. You know, for example, you cannot put negative numbers inside a square root or logarithm. You cannot put 0 in the denominator, so on and so forth. So by those rules, you can exclude everything which is not valid in math. For the 14.2, I know this is a part that you struggles a lot. So basically, I hope that I help you understand what is the intuitive idea of a limit. Basically, it is saying that a function approaches some number L whenever the point approaches some point AB or ABC, depending on your dimension. So it is saying that the function sort of behaves nicely when your xy, your domain, your argument goes through some point, okay? In a 1D case, it looks like this. So if x goes along the f of x, it goes along some point, then we're saying that this function has limit L at the point A, okay? The function approaches some value whenever the argument approaches some point. That is a definition of limit. And on the computational aspect, you will not be arguing whether, that's not a good sentence. So basically, whenever you are trying to prove a limit not exist, there's 2 ways to do that. One is to test 2 different paths, and you get different values of the limit. For example, one gives you 2 and one gives you 5. That is sort of the same idea as in the one-dimensional calculus when you're going the left and right limit to be different. And the second approach is to find a path that the limit does not exist. So for instance, if you find some path so that the limit goes up to infinity of minus infinity, then the function limit itself does not exist. And I won't ask you guys to prove a function limit exists via the absolute delta argument. That is too difficult. I introduced that just for completeness. However, there is a kind of problem that actually defines an actual limit for a 2D function, which is that if we're approaching xy towards 0, 0, then you can replace it to be the polar coordinate r cosine theta and r sine theta, and r goes to 0. Whenever this guy does not depend on theta, then that is a limit for this function. So basically saying that the limit is not dependent on theta means that you're going towards origin in different directions, right? So we're saying that whatever theta basically means that whatever path you're choosing, you still have the same limit. So as long as you can compute this using a one-dimensional limit calculus and you get some number which is independent of theta, then that'll be our corresponding limit of this two-dimensional function towards the origin. Okay? So this is the only case where you will be asked to compute the limit. And these two are the only possible strategy you have now to show that a limit does not exist. All right. So for partial derivatives, this is actually quite intuitive. So basically when you're differentiating some function with respect to x, then regard everything else, y, z, w, to be constants, and you do the ordinary single variable differentiation. And for higher order derivatives, you do the same thing. If you're doing xy, then you do x first and y. If you do yy, then you do y 3 times, and regard x, z, w to be constants. And there's a nice rule to memorize. This is basically the fundamental theorem of calculus that when you're differentiating this function under the integral sign, then you have this nice form, right? Okay, this is called Leibniz rule. So basically, 14.3 is not itself a big, important conceptual chapter. Most of the algebra there will be used in the following chapters. So this week, we have introduced 14.4, the tangent planes and linear approximation, which is how we define the differentiability for higher dimensional functions, right? Differentiability simply means that you have a tangent plane. And how is the tangent plane obtained? You can use this formula, right? The tangent plane for a particular function, z equals f of xy, at the point AB, f of AB will look like this. Z will be f of AB plus the first derivative fxab times x minus a plus fyab times y minus b. This will be the formula for a tangent plane near to the surface at the point. And we also have the corresponding linear approximation, which is basically a tangent plane, saying that if xy is close to AB, then we always have f of xy be close to Lxy, which is simply defined as the tangent plane. So you can always approximate a particular value for arguments near AB by this kind of formula. And obviously this also works for, oh, actually, no, this does not work for higher dimension. So okay, let me say this. So for example, if you're doing for a three-variable function, now it looks like this. I think I have put a exercise somewhere. It's exactly the same thing. This is approximately Lxyz, and that is f of ABC plus fx ABC, x minus a, fy, and fz. The same thing, okay? So that is called linear approximation. It works for every dimension. And then for the chain rule, there's actually not much to talk about. This section is very proof heavy. There's a lot of proof I recall in the lecture, but actually the concept is quite simple. So you apply the usual chain rule and you derive this kind of multivariable chain rule. So in this case, if z is a function of x and y, and x is a function of t and s, where y is a function of t and s too, then the differentiation of z with respect to t in this variable will be z to x first and then x to t. And don't forget, there's also a y, z to y, and y to t. The same thing happens for s, okay? Obviously, this generalized to higher dimension and higher orders, but basically that is what you have to memorize. Okay, and a slightly complicated concept is the implicit differentiation. So, for example, if we're dealing with a function, three-variable function, f of x, y, z being 0, which is the level set, right? The level set of this particular function. So it basically looks like a surface. And if we're wondering that whether on that surface, if there's a point so that the variable z will be a function of x and y, then you can do this kind of argument. So if f of ABC is 0, meaning that the point A and B and C lives on the surface, and that the partial derivative of f with respect to z is non-zero at ABC, then that means that z locally looks like a function of x and y, saying that z is f of xy. And that its derivative can be given by this nice formulas. Partial z, partial x is given by minus fx divided by minus fz, and partial z, partial y is given by minus fy divided by fz. And obviously the same argument works for a curve. So say you have a two-variable function and you're interested in its level set, then y can be locally solved as a function of x if fx for fy ab is non-zero. Okay, so make sure you understand how to apply this implicit function theorem, and that list of formulas are really, really useful. All right, the next section is on the directional derivatives and gradient vector. So we know that we have this unit notation nabla, defined to be the collection of the all partial derivatives of f. So in the two-dimensional case, it's fx and fy. In 3D, it's fx, fy, and z. And a directional derivative is basically how the function changes along that particular direction. So at a particular point and a particular direction, then the directional derivative will be given by nabla f dot product with the vector u. In this case, u is a unit vector. Okay, so whenever I'm speaking about some non-unit vector, say 0, 0, 2, then you always have to normalize it and then compute the directional derivative by this formula. Okay, and this is also very important. So there's very many directions along. There's a lot of directions in high-dimensional space, but the best direction of increasing is the direction of gradient. So I'm saying that the gradient basically points in a direction so that the maximum rate of the directional derivative occurs. And the maximum rate is basically the magnitude of the directional vector. Okay, that is basically because that the u here will be nabla f divided by its magnitude, right? However, nabla f dot nabla f is nabla f squared, and so it reduces to nabla f magnitude. So the maximum of the directional derivative along each direction will be magnitude of the nabla f in the direction of nabla f. And it will be minimized by minus nabla f with the value of minus magnitude of nabla f. Okay. And also with that kind of understanding, we actually have this very nice formula that is on a level surface, f of x, y, z being 0, then if the gradient vector nabla f of a, b, c is non-zero, then the equation of a tangent plane, okay, I have to fix this typo. The tangent plane is actually given by this guy. So basically, this is saying that this is a normal vector to the surface at the point ABC, right? So this actually sort of generalize what we have done here. So let's go back here. This can be actually understood by this equation, right? If we set f of x, y, z to be, okay, say f x, y minus z, then this graph is basically f x, y, z being 0, right? So we actually generalize this kind of notion. So instead of a graph, we can actually do that for different level surface. And this will be particularly important when we're discussing chapter 14.8, right? Okay, so now let's start like examples after reviewing concepts. So the first problem here is very classical. We have a problem that asks you for an equation of a plane that passes through 2 points, and we want to find a corresponding, and we also assume that there is some vector at j that is tangent to the plane. So let's recall, basically for a plane, you need two information: a point, which you have now 2, and you also need a normal vector, right? So we now have a tangent vector. To generate the normal vector, we need another tangent vector to perform the cross product. And that can be simply given by the difference of these two guys, right? If you have 2 points on a plane, then either direction gives you a tangent vector on the plane. So in this case, I subtract 201 from 332, and you get a tangent vector. So these two guys are orthogonal to the normal vector. You take the cross product, you get some vector, and you have the point 201, or this guy will do too. And then it's simply -1 comes from here, 1 comes from here, and -2 comes from here. This will be the equation for your tangent plane, right? This is a classical one. Okay, For the second problem, I asked you guys to find, there's 2 points and you want to find whether they intersect at some particular point. And you also have to find an equation for a plane that connects these two lines like this. I believe I have done similar problems like this in the lecture. So the solving is quite simple. You simply try to solve the corresponding three equations. So note that you're dealing with two variable but three equations, so there might not be a possible solution. But in this case, I already claimed that there is, and you have to find a solution. So you see that in this case, T and S can be solved by -2, 1, and the corresponding point is plugging these two parameters into the corresponding points, which you get 3, 1, 4. All right. And for the plane that contains these two guys, we already have a tangent vector here, right? The directional vector of this line is basically orthogonal to the normal vector on the plane. So this guy and this guy are what I'm interested in. We have 2, 1, 2 minus 1 minus 2 together with -1, 2, 2. That will be a choice of a normal vector, right? Taking cross product, you get this guy. And now you have a lot of points. In this case, I choose the point that we find here, 2 and 4. Actually, any points lie on this line and this line will do. So now we have 3, 1, 4, and the corresponding normal vector, 2, -2, and 3. And you get your equation for the plane. Right. Now, okay, so we're done with chapter 12. That is a preparational section, basically. Now we're in chapter 14. So in this case, f of x, y, z is given by square root of x plus square root of y, square root of z, and logarithm of 4 minus x squared, y squared, z squared. So the evaluation is quite direct. You simply plug 1 into everything, and you get 3 root 1 plus logarithm of 4 minus 3, which is log 1, which is 0. So you get 3. And for the domain, this is what I mentioned before. The natural restriction of root x, y, and z is that x and y and z have to be larger or equal to 0. They cannot be negative. And the restriction of the logarithm is that anything in the argument of logarithm has to be positive. So x squared plus y squared plus z squared has to be strictly, note that this is not strictly less or equal to, it's strictly less than 4. Okay? Because we cannot put 0 here, but we can put 0 here. So what is this? This is the first octant, right? And to be precise, it is the first octant containing the coordinate planes. So it is possible for you to have x equal to 0, y equal to 0, or z equal to 0. For this guy, this is a ball, right? A ball with center 0 and radius 2. And it does not contain the outmost layer. So x squared plus y squared plus z squared cannot be 4, okay? It has to be strictly less than 4. So geometrically, it looks like this. This is a domain. And you can sort of describe it by the intersection of the open ball. Open means that it does not contain the outer layer. So you can see that I wrote down here that it includes the coordinate planes, which is this, and this, but it does not include the spherical boundary, x squared plus y squared equals to 4. Okay? Right, so that's for the domain. And now into the section 14.2, limit and continuity. In this case, I want you to evaluate a limit or somehow show that it does not exist. So I mentioned this in the lecture that you can sort of figure out whether a limit exists or not by be careful on the degrees. In this case, the numerator and denominator both have degree 4. So they sort of cancel out the decay of x and y going to 0, sort of cancels out. It makes the limit not exist. In this case, I choose y equals mx, which is some straight line on the plane that passes through the origin. And if you plug y equals mx inside this equation, you can see that the limit along that particular line will be some constant. And that constant depends on m, depends on the direction, how we enter through the origin. So since the limit along different paths disagree, the limit does not exist, okay? You can also try something differently. So say if I choose to approach a known parabola like this, then you get x4 plus x5 divided by what it is, x6 plus x8, right? So see that in this case, the denominators have a higher degree in comparison to a numerator. So it actually goes up to plus minus infinity, actually, sorry, plus infinity, depending on the signature. But yeah, plus minus infinity when x goes to 0. So that is also a way to show that a limited sign exists by showing that the limited sign exists along some path. So let me recall you guys. You can either show that the limited sign exists along some path, or you show that the limit exists for two different paths, but they share a different limit. In this case, different ends. Right. So now for the second question, I asked you to evaluate this limit. So as I mentioned, there is sometimes actually there's this only time when you can compute the limit actually, which is when you're in a 2D setting and you're approaching the origin. So in this case, let us replace x and y to be r cosine r sine, and let us try to evaluate whether this exists or not. So x is r cosine, y is r sine, that makes this guy r squared, and this guy r squared. So you have r squared plus 1, r to the 4, r squared in the sign here, and for x5, it is r5 cosine theta, cosine 5 theta, sorry. And this guy is actually really nice because it reduces to r cosine to the 5 theta. And this actually goes to 0, whatever theta is, right? Because cosine is bounded by 1 and minus 1. So whatever theta is, this always goes to 0. And then for this guy, when r is 0, both the numerator and denominator goes to 0. So we can apply L'Hopital's rule in the one-dimensional setting. You get by chain rule 2r divided by r squared plus 1 minus 2r, that also comes from chain rule, cosine r squared divided by 4r cubed. And now it's algebra. So I divide both the numerator and denominator by 2r. So 2r is gone, 2r is gone, and the denominator is now 2r squared. And I also move the r squared plus 1, the denominator, into the big denominator. And again, let us see closely. If you plug in r to be 0, then the numerator is still 0. It's 1 minus 1. And the denominator is also 0. It's 0 times 1, right? So we can do L'Hopital's again, and you get this formula. And again, there is an extra 2r for each term in the numerator and denominator. So I cancels out 2r, cancels out 2r, and the denominator becomes 4r squared plus 2. Where in this case, we are fortunately done because both the numerator and denominator is equal to 0. And actually, it goes to minus 1 in the numerator and 2 in the denominator. So you get minus half. Obviously, minus half does not depend on theta. So this is actually a limit of this guy. Okay. So I would encourage you guys, I won't actually take point from this, but I would encourage you guys to write on the slide. Okay, whenever if you're computing a limit, then you have to state that, okay, this limit does not depend on theta. So that means that it is an actual limit. For instance, if you get the limit to be half minus half theta, then that means that this limit depends on the angle when we go through the origin. So that means that there is no limit because the limit behaves differently in each direction. Okay. All right. Now let us go through the differentiation part. So in this case, I just say sort of difficult example. So we have an integration of cosine t, where the lower bound is sine x and the upper bound is x plus y squared. And I want you guys to differentiate f respect to x and also respect to x twice. So we go back to the Leibniz formula. It's basically stating that if I want to differentiate with respect to x, then we treat y to be a constant, right? So basically, we plug the upper bound inside cosine, and we differentiate the upper bound by x. The same thing happens for the lower bound. We plug the lower bound and differentiate by x. And that is just algebra and single variable calculus. And for the second derivative, you simply apply the differentiation to this formula again. So for this guy, you have minus sine. For this guy, you have to apply a product rule. So in the first term, you have sine x and cosine squared. This comes from this guy taking product with the differentiation of sine. So that's cosine squared. And the second guy is cosine sine. The differentiation of this guy is minus sine. So you get a minus minus becomes a plus. Okay, simple chain rule. Simple product rule. Right, so that's kind of like exercise on differentiation. Integral. Okay, so this is a classical one. Now we have a function, two variable function, fxy being 1 minus xy cosine pi y. And I want to find a linear approximation, which is basically a tangent plane at the point 1, 1, and we want to use it to approximate a value which has an argument similar to 1, 1, 1.02 and 0.97. So first of all, obviously we have to find the tangent plane. The derivative of f with respect to x gives us minus y cosine pi y. So plugging in 1, 1, we have 1, and the same thing happens for y, and it's also y. So the linear approximation is 2. The 2 comes from here, f1y is 2, plus x minus 1 plus y minus 1. So we can estimate this value by plugging in x to be 1.02 and y being 0.97. And then you see that it is 1.99. Okay, approximate. The tangent plane actually has a value 1.99 at the point here. And we know that tangent plane locally looks like a surface, so this approximately is 1.99. Right. Now we're into the chain rule part. So this is an exercise from the textbook. So f is differentiable in x and y, and g of uv is defined to be this function. G of uv is f of eu plus sine v, eu plus cosine v. So this is a classical chain rule. You have two variables, x and y, where each of them are functions of u and v. So by their definition, GU00 is defined to be fx first, and then x divided by u. So that's EU. And fy and y divided by y differentiated by u. So that's this guy. And we'll plug uv to be 0. Which eventually you get fx12 and fy12. Where by the table, this guy is here, 2, and this guy is 5. So you get 7. And same thing happens for v. So the only difference is that we're differentiating x by v here, which you get cosine v, and differentiate this guy by v here, so you get minus sine v. And eventually, by plugging u and v to be 0, 0, you get fx12, fy12, and 1 and 0, which gives us 2 in a v partial derivative. Right? This is a classical application. And now we are into the implicit differentiation, which is a little bit more technical. So let me go through this slowly. So we have a 3-variable equation, yz plus x ln y plus x squared plus z equal to z squared. The first question asks you to show that z is locally a function of x and y near 2, 1, 1. So there is a lot of big words like locally solvable. This sounds very complicated, but basically I want you guys to do is that to show that fz at the point 2 and y is non-zero. That shows that z is the function of x and y, okay? So now we can rewrite this into a level set, right? By moving everything to the right or left on the equation, doesn't matter. So in this case, I move z squared to the left-hand side. You get yz plus x ln y plus x squared minus z squared. So implicit function theorem tells us that if you differentiate it respect to z and evaluate at the point is not 0, then it is locally solvable, okay? So that is all you have to do. Differentiate this guy with respect to z, then you get y minus 2z, and that is solvable. That is non-zero when you plug in 2, 1, 1. And now if you want to differentiate z with respect to x, then according to our formula, we know that this guy will be fx divided by fz, right? Fx is simply ln y plus 2x. And fz, we have it here, it's y minus 2z. So plugging the corresponding point, 2 and 1, we get 4. And this is a new particular type of problem, but it's actually not that difficult. So how do we differentiate z with respect to x twice? So basically that is differentiate z with respect to x first, which is this guy, and differentiate once again, right? And now it's simple quotient rule. So we have the quotient, the denominator squared. We differentiate the numerator first, you multiply by the denominator. Note that there is a minus sign here, be careful. And you differentiate the denominator and you multiply the numerator. So this guy is quite simple. This guy is just 2 times y minus 2z, right? And this guy is simple, ln y plus 2x. Now, this guy, the derivative of y with respect to x is 0 because x and y are independent variables, right? We are solving z in terms of x and y. And differentiate z with respect to x is simply just here. This is the same thing as this guy, right? So how do we evaluate this guy? You see that in the first term here, you have 2 times y minus 2z. So that's minus 2, right? Actually, yeah, minus 2. And this guy, sorry. And this guy is ln 1 plus 2 times 2. So that's 4. And what is this guy? So this is minus 2 times our previous answer here, right? Times 8. times 4, sorry. So that's minus 8. So eventually you have minus 2 minus 4 times minus 8. That is 30. And you have an extra minus sign here, and denominator is 1, so you get minus 30. Okay? So you can see that you can actually do every order of differentiation for an implicitly defined function, just that you're already aware about the first derivative. So you can actually try the third derivative. You can get a similar answer by the first and the second derivative, okay? Right. So yeah, this is a particular different example. I don't think I have presented this before, but not this. So you can see how that works, okay? Right. So for problem 10, we're asking at which direction is the fastest change of this function, f of xy being I plus j. So that is basically saying we already know that this whole sentence means that you're finding the direction of the gradient, right? So first of all, let us find a gradient. Gradient of f of xy is given by 2x minus 2 and 2y minus 4. Yeah, 2x minus 4, okay. And we basically require that this guy is parallel to this guy. So 1, 1, right? That is what the fastest change of direction means. Because the fastest change of direction, direction of fastest change is basically a gradient vector. So setting this two guy to be equal, which is basically what we're saying that this have to be parallel to this, then you have y equals x plus 1. So along the line, x plus 1, this guy always have the fastest increasing direction to be I plus j. Okay? All right. So just to be clear, say on the point 2, 3, the fastest change of direction will be something like 1, 2, and 1, 2. Okay? That is what we had done. All right. So for our last problem, problem 11, we have an implicitly defined surface x squared minus y squared plus xz plus xy minus 4z squared equals to 5. So that is also some level surface of some function, right? So the first problem is actually quite simple. We simply want to verify whether 2, 1, 0 lies on S. So you plug everything inside and you verify the equation is true. Obviously, for convenient reasons, I set up the function f of x, y, z to be moving this 5 to the left-hand side. And so this surface can be represented as f x, y, z being 0, right? Okay, so now the second problem asks us to find the tangent plane of this surface at the point 2, 1, 0. So first of all, let us compute the gradient, which you get by doing direct algebra 502. So 502 will be the normal vector of the tangent plane here, right? Let us recall this. This is a very important formula. Whenever you have an implicitly defined surface that looks like this, then nabla or gradient of ABC will always be the normal vector at the point ABC of the tangent plane. So this will be your normal vector. And therefore, the corresponding equation will be this guy dot x minus a, y minus b, z minus c to be 0. In this case, I choose ABC to be 2, 1, 0. So you get this guy. And then it simplifies to 5x plus 2z equal to 0. That'll be a tangent plane of this particular surface, which is a level set at the point 2, 1, 0. Right? Okay. And as I mentioned, there is a lot of exercise here, which I deem to be useful for you guys to prepare your midterms. There's actually a lot of them. Okay. So yeah, as I mentioned, I would recommend you to do this kind of studying steps. First, review the concept by trying to sort of determine yourself which concept are you not really familiar with. If you're not, then you go to the lecture. You try to see how I do problems and investigate the concept and define something that is crucial for our study. After understanding the concept, you work up assignments, okay? Which I presume you guys have done already on the suggested assignment. And here I also provide some different exercise, which you can look through. And thirdly, try to do problems without looking at my solutions. So in this case, one of the maybe best suggestions to do this part of the exercise And if you do that, obviously I will upload the answer key shortly. So after you finish the reviewing of concept and the reviewing of the exist exercise and the quizzes, then I encourage you to do this new exercises and do that for yourself, meaning that try to write everything down clearly, and it should be persuasive to both you and me. Okay. All right. Um, I would say that will be all. So that is for our lecture 12, midterm one review. And I will see you guys in the next video on the introduction of maximum and minimum values. So see you guys and good luck on the midterms.